Okay, it's 10:18. So I'm going to kick this thing off. First off, everybody, thanks for joining. I know time's valuable to all of you, and appreciate you taking time out of your busy day to spend an hour with Dan Groninger, Matt Skinner, and I. And as you know, we recently introduced the 2.0 release of Mentor UT, which gives us a lot of enhanced capabilities and an overall faster operation by moving to the Linux platform. So what we're going to be doing this morning is I've asked Dan to do kind of a live WebEx walking through kind of the generic Mentor UT application. So Dan's going to be walking through that. That should take about 35 minutes. I want this to kind of be a interactive session because it's a fairly small group. It's the folks on a North American sales team. So if you could, just to keep the background noise down, if you could mute your phones, and then if you have any questions while Dan's talking or Matt's talking, please unmute and just ask the question. So Dan's going to walk through this first application, kind of the generic or general one, and then sure, buddy.
All right, and can everyone see my my screen? I have a camera pointed at some equipment on my desk on the left, and the Mentor screen on the right. Everybody have that?
Yep.
Okay.
Good, Dan.
All right, so I'm going to work through an app that we call the Phaser XS app. Tried to duplicate a lot of the functionalities of the Phaser, set up for basic angle beam inspection. It's one of the golden apps that goes with Rev 2.0. So we'll launch the app. And for those of you who haven't seen 2.0 yet, I think you'll be pleasantly surprised by how much more responsive it is than the previous versions of the Mentor. When we switched to the Linux operating system, it allowed us to access more memory and gave us a couple of other features that make things a lot faster and more responsive. So I'm going to show you the quick start version of this first, and then we'll come back and work through the calibration step by step. So I've already been through all the calibrations and saved my basic setup. So I'm just going to go to Files menu, Load Settings, and I have a file called Calibrated Weld Scan. We'll load that, and it'll take me straight to the scanning panel. Okay. As you can see, we're all set up here. I've got the weld overlay enabled. I've got my gates positioned. I've done all my calibrations. And I have it in timed scan mode. I'm guessing most of you, when you're doing demos and so on, won't want to drag along a lot of encoder equipment. Later during the encoder calibration part of the demonstration, I have an encoder here, and I'll show you how that works. But for now, I'm just going to do a quick hand scan. I have a weld sample here. It's a 19 millimeters thick piece of steel, multiple laid up V-weld. I have a little edge guide that I threw together in my shop to help me maintain setback and everything. But like I say, I've been all through the calibrations, so I'm just ready to go scan. So I'll start to scan. It's time to pull along here, along the length of the probe, or along the length of the part. I'll stop my scan. So I've got three indications on the in this weld. The first indication is right here at towards the beginning. That is a lack of fusion down at the bottom of the weld, at the bottom of the V. In the middle here, I've got some porosity and indications on the near surface of the weld. And up here at this end, there's a crack that's up on the top surface right along the edge of the weld here. I found that crack pretty readily with eddy current as well as UT, so it comes right to the surface and penetrates in a little bit. So if I grab my crosshairs here, go back and select the area where I have that lack of fusion at the bottom of the weld. Let's blow this up to full screen so that we can see what's going on a little bit better. You can see the V's.
Hey, Dan, you're frozen up. Dan, you're frozen up on this end here. Maybe you should just stop the recording if that's using the bandwidth. Oh, there you go.
Okay. Are we back and moving again?
You're back on. Yeah.
Okay. I suspect that's more just WebEx behavior than anything else. But all right. So anyway, now we have full screen. We have the purple lines on here. The violet lines are the weld overlay. So you can see we're looking at most of 4 times the depth of the part. So we have the V, the thickness of the part down to about here. I've got my gate starting right at the bottom surface of the weld. Then you'll notice the part is flipped over, inverted. So we go top to bottom, bottom to top, top to bottom, bottom almost all the way to the top again. And we notice we've got a nice bright indication right at the bottom of the weld, and that is in fact that lack of fusion at the bottom of the weld. If I come out here and scan over to this next indication, my crosshair, come down, you'll see there's a little bit of slag or an inclusion right on the grind line of the weld about halfway up. And if I come over here, there's that nasty crack that's right on the surface. It's actually a little bit to the near side of the weld in the base metal. So it's outside of the outline of the weld. You know, our index, my distance might be off just a hair, but that shows you how you can pretty readily find, again, indications, middle of the weld, bottom of the weld, and up near the surface. And as I move the crosshairs, just like before, I'm going to get the E scan and the A scan that goes with wherever that crosshair is positioned. So wherever I put the vertical crosshair is going to give me the E scan that goes with that sweep. And then from there, I can select the A scan that goes with the horizontal crosshair. So, do we want to take any questions on what we've seen so far? Nope. Okay. So that was, again, that was the quick start version of running the app. So now let's exit out of here. Yeah, we don't need to save that. Okay. And we'll start the app another time. And this time we're going to go step by step through the entire setup and the calibrations. Okay. So step 1 of the app is just a basic welcome panel. Step 2, I call this the initial setup panel. And the reason we created this panel is when you're setting up to do a test like this, there's a whole lot of things that are fixed numbers that you're going to pull off a data sheet or off a drawing of your part, that sort of thing. So I just kind of went step by step, 1, 2, 3, 4, 5, more or less in the order in which you would want to configure the instrument to do the test. So in step 1, we have all the probe parameters. So we've got a menu here. It's a 1D flat array, 5 meg, and typically you would find that information on written on a label that would be on the connector end. I'm not sure why we do it this way, but we typically put the label on the face of the connector where it bolts onto the instrument. Not very convenient. So like you see, I took a label maker and reproduced all that information on the outside of my label. So I go in and enter all that. So next step is to define the wedge. And most of our phased array wedges, see if we can zoom in on this a little bit, will have the critical information engraved right on the wedge, usually on one side in imperial units and on the other side in metric units. So we have the incident angle, the Z offset, wedge front distance, all of that engraved on the wedge, part number on the back of the wedge back here. For the part, there's a couple of items on here. The part thickness. In this case, I have a nice chunk of steel here, and I've measured this. It's 19 millimeters thick. Of course, I wouldn't use a ruler. I'd grab my CL5 and take that measurement. But so anyway, 19 millimeters thick. Part velocity. This one trips me up all the time. You guys are probably smarter than I am, but I can't tell you how many times I put longitudinal velocity for steel in here when I'm doing an angle beam sweep. So make sure you use the shear velocity for steel when you're setting this up. I believe I put a note over here to the side to be careful of that. And the ref 1 and ref 2 are distances that we're going to use in our calibration block for different steps of the calibration. I built this app mainly around the DSC test block because it's a nice size to carry with you when you're going out to do demos and so on. I found it to be a bit of a pain to work with the DSC block because it never wants to sit nice on the desk. So cut out a little holder out of a scrap of 2x that I had laying around. But here I've made use of the fact that there's 2 radii on the DSC block. When I'm on the block pointed that direction, I have a 1-inch radius, and I also get an echo from here out to this radius and back to there. So I've got a 1-inch path and a 5-inch path, and I'll be able to see both of those echoes without moving the probe. And that comes in very handy later when we do the velocity calibration. So I set up for 1-inch, 25.4 millimeters, 5-inch, 127 millimeters. Okay. For sweep and scan, I told it that I want to do a sector sweep, and we're going to do a line scan, meaning we'll either use timed or just one axis of encoding later on. So the scan pattern has to do with how you're going to move the probe, and the scan type has to do with how the probe is going to scan. Are you going to do a linear scan like you do in a corrosion test, or are we going to do a sector scan where we're sweeping through a range of angles? Okay. And then if I'm going to set up a sector, you see I have a little bit of a branch in my path here. If I'm going to do a sector, I have one menu, and this is what we're going to do. So we're going to do a 32 element aperture. This is another place where I've seen a number of people trip up a little bit when they're setting up a scan pattern. When you're doing a corrosion linear scan, you'll frequently use a small aperture, like 3 elements or 5 elements, something like that, and step it along the length of the probe to do your scan. In a sector scan, the more elements that you use in your aperture, the more accurate your steering and focusing are going to be. So if you accidentally define a 3-element aperture and try to steer that through some range of angles, it really doesn't work. you don't have enough elements involved in the aperture to accurately produce an angle. It's going to be pretty much of a weak straight beam that's going to refract at just whatever angle your probe is. Okay, so in this case, I used all 32 elements that I have available in the probe. I've told it I want to sweep 35 to 70 in 1 degree steps, and I'm going to focus out 40 millimeters into the part. Okay, for a linear sweep, we're not going to make use of this, but there's other parameters available if you really did want to set up a linear. Okay. So that's all the things that I know from either looking at labels, engraving, either measurements or drawings of my part. A little bit later, we'll look at how the weld overlay is done. There again, you'll need to know from a specifications document that instructed the welder how to make the weld, or just from common practice, you'll know what the shapes are and the angles there. Okay. So now if we start through our calibrations, first thing we want to know is, do we have a good probe or not? All right, are all of the elements of the probe alive and working? So for the dead element check, what we've done is tell it we want to scan a 1 element aperture across the face of the probe. And since we're already coupled to the wedge, what that's going to do is the first element on this probe, the first element is the low side of the wedge. It's closest to the surface. With just a 1 element aperture, there's no steering, so we're just going to get a reflection off the bottom face of the wedge. And you'll see as we go up the element numbers, we get further and further away from the face of the wedge. Okay, now I notice if I move my beam selector back and forth, I notice right now that none of my elements are making a tall enough echo to break into gate A, and we need them to be. We need to get this green line up into the purple band. So I'm going to open up my gain, and I'm just going to increase the gain a little bit. Okay. And what the dead element test does is it's going to look at every element. It's going to pick the hottest element, and it's going to say, are all my elements within 6 dB of the hottest? Do I have any weak ones or dead ones? And right now, this looks pretty good. So if I hit calibration, it says, yep, all your elements are alive. That probe's good. Okay. Now, next step in our calibration process is to look at all the beams and get the delay, the probe delay for every beam normalized so we have a nice neat arc. Now you notice I have a drawing here of the probe sitting on the DSC block. It's a little deceiving because the only drawing I had available of the DSC block showed an arrow pointing at that radius, but if you notice the way I have the probe drawn sitting on top, it's pointing at the short radius. So I say place it on the block as shown. You see as I move back and forth, I'm getting a nice neat arc as I sweep through all of my angles. But the arc isn't quite parallel to my gate bars. Okay, we'll make that bigger so we can see it better. All right, and that means the delay on each one of the beams is a little bit different as you step through. So we're going to correct for that by doing a delay calibration. So if I hit cal, now you notice my delays are all parallel to the gates. Okay, so it calculated the delay on every individual beam and adjusted all the beam delays to give us an equal neat arc there. Okay.
Dan, this is Scott.
Yeah.
Can I stop you and ask you a question real quick?
Sure.
So
sure.
You said the calculation is for each beam. Is that actually done, or is that interpolated somehow?
No, that's actually done.
Beams individually,
nope.
They're all independent zeros?
Yes. Yep, the zero's done on each individual beam, and that's, yeah, it's not interpolated. We don't, in this case, we don't take one measurement and interpolate them. Okay. So now,
Thank you.
yep, any other questions? Okay.
Not right now.
All right, so if we skip to the next step, we're going to do the 2-point velocity calibration. And you notice everything's set up already because I told it about the 1-inch and the 5-inch paths, SREF1 and SREF2 at 1-inch and 5-inch. Just with my probe sitting on the block, I've got both echoes in place. And now velocity, you choose one beam to do the velocity calibration because we assume that all the beams are going through the same piece of material. You only need to do this once. So there's one velocity calculation for everything, and it's taken off of whatever beam you have selected. So you notice as I sweep my beam selector along, some of my steeper angle beams aren't picking up that 5-inch radius very well. So I'm just going to pick one here in the middle. It gives me a nice neat echo in both A and B. So it says, show me the 25 millimeter, show me the 127 millimeter, and my velocity is 3234. So normally I'd expect in steel about 3250, so we're pretty much right on the money there. Okay. Now the next step is TCG. And in this case, we've told it we want to do you have some choices here. In this case, we've told it that we want to do a radius reflector type. Again, using this DSC block, I'm going to shoot at the radius at the end to normalize the amplitude on my beams. Okay. And my first point's at 25 millimeters, and then we're going to turn around and do one at, I believe it's 75. We'll look at that when it comes up. But the first point we're going to do with the probe pointed this direction. Second point, we're going to turn the probe around and shoot at the other radius. Okay, so let's see here. Close that menu. We'll do, wants to start the calibration, show me 0.1. It says, yep, got it. Now turn your probe around, and you'll notice gate A was set up over that echo for the first point. Now it's expecting the next point out at 75, so we'll turn the probe around, and we'll peek up on that echo. And we're all done. So there was 2 points of TCG calibration. Again, we use the radius reflectors for simplicity. All of the beams were individually calibrated for TCG. So you notice we have very neat, consistent amplitude for that reflector on the beams. For all beams, if we flip it around the other way, there's our short radius, and again, very consistent amplitudes across. Okay, if I move my gate down here, that's pretty consistent across my amplitude scan up top. Okay, so that was TCG.
Hey Dan, now that's for a selected angle, not for all beams, right? Not for all angles.
No, that's just the opposite, Scott. When we do the TCG, and that's why I chose the radius reflectors there, so that all beams could see the same reflector without having to move the probe around. If you choose side drilled hole as a reflector, first of all, you need a standard that's got a side drilled hole that's kind of out in the open without any corners or other reflectors around it. And then you need to slide the probe back and forth so that all of your beams have a chance to see that side drilled hole in the same way. Because the TCG calibration is done for every individual beam. Okay, so dead element check looks at every individual beam. Delay looks at every individual beam. TCG looks at every individual beam. The auto 80 and the velocity are going to look at your selected beam alone and then apply that same measurement to all the beams. So when you mentioned interpolation before, it's not exactly interpolation. We're going to add the same value to all beams, but velocity and auto 80 are done on the selected beam, while TCG and delay happen on every individual beam. Okay, so this is the, and oh, before we go on, any other questions? Okay, so now we're going to do a sensitivity check, and for this, this makes use of the auto 80. And as I mentioned before, this function works on the selected beam, but then we'll apply that same offset. It's you can think of it as a TCG offset, if you will, since we've already calculated the sensitivity curves for each individual beam. What we're going to do now is we're going to point one selected beam at the side drilled hole in our block, peek up on that, and we're going to say, I want to see how big, there's our 1/8 inch hole. I'll make this big so we can see it. So right there is our 1/8 inch side drilled hole. So that is on, right now we have that peaked up on that beam, okay? And I say, when I hit the cal button, it's going to calculate the gain offset needed to be added to the TCG curve to get that reflector at 80%, because 80% is the value that I've chosen. But now, as I move such that that is shown that I have the different beams are seeing the hole, I should get a consistent amplitude for that hole across the range of all the beams. Does that make sense to everyone?
So if you go to your A scan right there, when you go to those different angles, are you still getting 80% off even off the selected beam that you're at?
Well, as I move the A scan is always going to reflect whatever the
Right.
selected
So
beam
you're
is.
80%.
Yeah. So, you know, as I walk the indication to a different beam, of course I lose it on that A scan. Let me get a hold of the beam selector. Let's see, there's your 80, 90%. If I bring it over here and bring that back, you know, it's all pretty sensitive to the alignment of the probe and coupling pressure and stuff too, but you can see how it's pretty well on for all the different
But if
beams.
you did, Dan, if you did sensitivity with all angles versus a selected angle, shouldn't that 80% be more accurate across all angles though?
The problem that you run into is, especially when you're trying to hit a side drilled hole like this, yes, in theory you could do that, and you slide back and forth and you try to pick it up, but as you saw here, I have so much variation from a little bit of twist in the probe. See how much that dances around with just a little? It's so hard to combine moving a probe with a sensitivity calibration. You can set up the TCG calibration to use the side drilled hole and scan back and forth. But what I've run into very consistently is almost every standard that we have that involves a side drilled hole, as soon as you get the probe positioned this way along the direction of the scan so that you've got the gate seeing the side drilled hole neatly, one of the other beams is picking up something else. Like if you look on the sector scan here, Yeah, there's the side drilled hole that I'm interested in up here. But you notice I've also got some stuff out here that's coming from the geometry of the part. Some of my beams are picking up this corner down here, while other beams are picking up the side drilled hole. And that tends to just really hose up what the gates are seeing at any given time. So,
Hey, Dan.
yeah.
Dan, this is Bruce Newmoss.
Mm-hmm.
I'd love the fact that you can do that on a curved radius like that, but none of the codes or specifications set up a deck that way. They all set it up off of a side drill hole or an ID OD notch or a flat bottom hole. And going back and looking, and I was with Matt a couple weeks ago, and we were having with the nav shift block. I was having a hard time getting any DAC to draw over 3/4 of an inch of sound path. And that was the problem we ran into with the laser, and we had to add that function called cycle gain. And if we can't do a side drill hole with at least 2 inches of sound, maybe 2.5, 3 inches of sound path, you might as well not even take it to market. And I've been having a hard time getting that DAC to draw much further than 3/4 of an inch out. And I think that's something somebody needs to focus on before we go up. And we stepped in mud doing this with the laser. I don't want to do it with this.
Okay, so Matt, you're on the line. Have you put that in the works for the team to create such a feature?
Yeah, I have actually, and it's I'm trying to think of the best way to explain it. So I hear what you're saying. I understand what you're saying. Obviously, Bruce, we were together. So what's going on when you record the TCG is it's unclear because it says record point 1 and you do it, and then it's tough to know when you're done doing it. And so there's a sequence of button presses between you record it, you hit the calipers, you record it again, you hit the calipers, and you just basically, because it's so unclear, you just keep doing that until it goes on to point 2, and then it goes on to 3, 4, 5, however many points you have at whatever depth you have, and then all of a sudden it says completed. And what's going on is you're doing it, and then it's adjusting the gain for every beam, and then it's checking it. And so we are going to change the way that presents itself, and it is actually capable of doing it. What the problem is, a user is not going to be, especially not a user that doesn't have a lot of stick time with it, is not going to be capable of doing it because it's misleading. So what happens, like I said, you hit the caliper, you start recording, it records where it's at currently. You hit it again, and it says record, and you hit it again, and you just keep doing that till all of a sudden it advances to the next point, and it's unclear as to what just happened. So yeah, we know that's a problem we have, but the instrument is actually capable, which is good because we don't have to redesign electronics, but we do need to redesign the way it tells you what it's doing. Does that help explain the phenomenon?
The other question I have, Matt, is the machine capable of enough, I guess, gain or gain for the higher angle beam at the longer sound path distance, because that's where we always fell into trouble. And I can't get a DAC drawn on a nav shift block over an inch, the inch deep sound the side drill hole. I've spent an hour on it. I couldn't get it. All right. Okay.
Yeah. The machine is capable. It's a function of the user interface. And we know we do improvement as far as what's that?
Well, I'm not.
Well, I mean the thing. This has been a challenge, I'll say, with every device on the market. Just trying to simplify this stuff. We've gotten close here and there, but at the end of the day, it's never been as easy as just a calibrating thickness gauge, which ultimately is what we'd like to have. That being said, the pulsar in this device is different than everything we've ever had. So it has different characteristics that we're just learning what that means and how they're going to react. But you know, it's a noted point. The device is capable of doing it. We just have to change the way the presentation of it to make it easier. And the first thing you have to overcome, which we've all learned already, everyone on this call, is the darn skew in your hand. You got to take that out of the equation. And we do that, you know, we can lay it on the side or put a guide on it or whatever. And so, you know, once we figure that out, we go, okay, now. And then it's a matter of moving the gate in. So if you tighten up the gate, like you saw, we tighten up the gate as much as we can. We give us as much tolerance as we're allowed to have. And when you start, it's good to bump that way out just to get the finesse right. And then you can begin to bring the tolerance in. So we need to change the wording, which is similar to the way we skew our hand, so that we get those two variables eliminated. And then we go, okay, is this something the instrument's really just simply capable of, and we just had to make some adjustments to the way we approach it, or do we need some kind of, and I do not want to go to a cycle game type situation. I'm not going to go there. So there is work.
Another question, based on what Dan said, even on the nav shift block, you do start running into the adjacent holes that are drilled, and it does screw things up. With any other manufacturer, does anybody else know, has anybody ever developed like a blocking gate, block out that signal that you know is there, but you don't want to record it?
What we'll do, we'll do what everyone else did. Is so if you're sweeping, say 30 to 70, which would be a big range, you go 30 to 45, and then it does 45 to 60, and then it does 60 to 70 in different sections. So it's effectively a blocking gate. The problem is if you have any variation when you go section to section, you get a very crisp line along that angle that ultimately doesn't hurt your inspection. It just makes the picture look a little worse. But that's really the only way around that.
Okay.
Yeah, either that or you need a physically very large block where you can separate the indications far enough that, you know, you're only seeing one indication on the whole sweep of angles at a time. Because, you know, right now I'm looking at that side drilled hole on which beam, the 45-degree beam. But you notice out here, my shallower beams are already picking up some geometry indication that's up in the gate. And you notice I'm getting an indication on those from that as big as the primary indicator I'm interested in. So this was the most useful approach for this block, put it that way.
I just want to get that in before I leave. I've got to drop off here, so thanks, guys.
Okay.
Thanks, Bruce. I guess, I don't know if Bruce is still on, but Dave, would you mind, this is a good question. It's a good thing to not completely answer. However, I think in the spirit of completely answering it, would you mind setting like a session just for, you know, TCG on a 2-inch deep reflector? For maybe a week after next, and we'll go through just that, because it's a great discussion, and it's an area where if we do it right, we can really show off. If we do it wrong, we're gonna struggle in one more area. So, you know,
another nice feature on that, if we're talking about the TCG echoes, is maybe to be able to develop in the software where we can actually recognize the geometry echo, touch on the screen to ignore it, and it grays out that group of pixels, right? Or
or the square,
right?
Or something. Yeah, that'd be great.
That would be a 10 point over what's out there now.
I think the Gecko does that, where they actually window in on side drill holes, and they calibrate on that. I think that's out there, I believe.
Okay. Yeah, I don't know, but either way, it'd be nice to have, just like we do the zoom on the C-scan. You could do it basically a zoom box and say, don't pay attention to that. So yeah, we'll see what it would take to get that done.
Okay. So should we move ahead?
Yep, let's keep plowing ahead
Okay.
there.
All right, so I just skipped to the next panel, which is we've done all of our calibrations, and we're just going to do some quick hand scanning. So I've got a sector and an A scan. So scan along. Oh, there's something interesting. I've already got the selected beam up there, but yeah, I can select our beam. So we have our A scan, and that's the lack of fusion down at the bottom. If I scan along here a little more, oh, there's next indication. Bring my beam selector down. There's the that bit of slag or inclusion. Come on out here. There's my surface breaking crack. If I wanted to tweak up the weld overlay, I've got all the controls on a menu here for that. Alpha is the angle of the weld. We have some reference material on the back panel here that we can look at that tells you what each one of the different dimensions are, the A, the B, the C, alpha, beta angles. Index offset is how far is the face of my probe back from the center line of the weld. In this case, it actually is 30 millimeters back from the center line of the weld, so that's what I have dialed in. If I move the probe back and forth this way, I can change my index offset to make up for that. Okay, and that'll position.
Is there any plan for, if you have a gated area right there, actually go to the highest amplitude response within your gate instead of having to move the cursor over to it?
There is. I have actually seen that working. I forget if it was just in one of the prototype builds, or if there's a control that I don't know about right off the top of my head to activate that, but I have seen it working.
Yeah, there's well over 200, like 260 something planned features that keep getting bumped around and slotted around. That particular one, we actually classified it as a bug. Gate tracking of the highest amplitude is something we should have. So that's in a set of bugs that will be added. And I don't think that one got into 2.1. That may be as early as 2.2. Like Dan said, we've had a prototype of it. But yeah, there's plans. What I tell you is when we get it. But yeah, it's something we should have.
Okay, so I'm going to move on from this panel quick. I just wanted to show you the encoder calibration process. Here we're just doing everything timed, but I do happen to have an encoder plugged in. And what I'm going to do here is I'm going to say I just want to do one axis. So I'm just going to do the scan axis of encoding. And I'm going to move an expected distance of 200 millimeters. Okay. And I'll put my probe, or put my encoder on my ruler here. I'll say there's 0. It says move the expected distance. I'm going to move it down here 200 millimeters. Do that. I'm going to move it back. Hit calibrate again. It says, yep, we're all calibrated. And I clear my message. So if I look at the reference X position here, get that to 0. Can move out here. There's my 200 millimeters. Back to 0. Okay, so the encoder calibration is that simple. I tried to put a drawing here with reference materials that show what all the different axes mean, how to move if we were doing a 2D calibration, all that. Next panel is a scan panel that has the C-scan capabilities. So all of the analysis features, recording features, analysis features that you were used to with the corrosion version are still here. So we can go back and review. Okay. So everything that you were accustomed to before in terms of analysis is still here. The weld overlay has been added. There are some new measurement features on the sector scan. You can turn on multiple cursors and crosshairs, and there's all sorts of measurements that can be done there. I think we'll save that maybe for another session. We'll do a session just on the analysis features. Okay. And the very last panel on here is, I think, where are we here? So we're going to do clear. Yes. Okay. Next panel. Let's see. Is explanation. It's a PDF viewer with an explanation of the weld overlay controls. Okay. Because the various dimension names aren't terribly intuitive, so we added this material to help cover that explanation. And what's our next panel? Oh, the next panel is just a reference drawing of the DSC block. Since so much of this app is built around, all the calibrations are built around the block, we added the drawings and dimensions of the DSC block. Okay. So that's the app. I think I've run a little bit over with the questions and just talking too much. Dave, how about,
No problem.
I guess we're going to hand it to Matt now.
Yeah, I think let's hand it to Matt. I'd ask Matt